Thank you. So I appreciate the invitation for many reasons. One reason I can see this is a very interdisciplinary group, and it's always fun to speak to a broad audience. This is one of the reasons that I got into this particular field. Okay, so I'm going to be talking in a broad sense about the impact of quantum physics on information science. And this is a good time to be talking about this because we're in the middle of what some people are calling a quantum revolution. Some people say it's the second quantum revolution, some people say it's the third, probably just depends on where you're coming from. But it is a revolution in the sense that ideas that have been developed in the abstract for a few decades now are being put into practice. So we're seeing prototype quantum computing devices and also prototype quantum networks opening up new avenues for the use of the unique properties of quantum physics to do things with information that we couldn't necessarily do before. There's lots of good surveys about this. I've highlighted a few here from the last few years. So I would say that among areas of computer science, one of the areas that is most impacted by this change is the field of cryptography. And that fact has a lot to do with one paper in particular, and that is this paper from 1994 by Peter Shor, Algorithms for Quantum Computing, Discrete Logarithms and Factoring. This showed the amazing results that a theoretical quantum computer could factor a number in polynomial time. And when we say polynomial, we mean polynomial in the number of digits of that number. Depending on your perspective, that could be very bad news because factoring is the basis for RSA encryption, widely used encryption. And if that problem one day turns out not to be a hard problem, then that encryption is insecure. So there's this threat, which in the past has been pretty abstract. In the more recent past and the present, it's starting to look less abstract. So the question is, how does cryptography react to that? So there are two fairly different ways, even though they have similar titles, ways that cryptography can evolve in reaction to the threat from quantum computing, and that is quantum cryptography and post-quantum cryptography. So what these refer to are, so the first refers to cryptography based on actually quantum computing devices themselves. So we figure since the threat comes from quantum computers, let's try to use quantum to develop something new. And this gives us a fundamentally different type of security, which we're going to see kind of unfold in this talk, than ordinary digital cryptography gives us. The other side is something Liana just mentioned, which is post-quantum cryptography. And that is, rather than rebuilding everything from the ground up, let's just reinvent some new classical algorithms that can be run on ordinary computers that are resistant to quantum computers. And that means in particular avoiding factoring, because we know factoring is bad if a quantum computer is built. Both very interesting topics. This one is going to be my focus for today. Post-quantum cryptography, if anybody's interested in it, there's lots of great stuff on the internet, in particular on NIST's website. If you Google post-quantum cryptography project at NIST, there's lots of good stuff there. And there was actually the PQ crypto conference just happened online, and talks are available online. But quantum cryptography is going to be my focus today. I find it a very interesting subject because I'm a mathematician, and the task of mapping out the possibilities within this subject raises a lot of interesting theoretical and mathematical problems. So kind of the overall project that I'm interested in is the question of creating a new map of what is possible and what is impossible in the domain of cryptography. So now that we have introduced the new possibility of using quantum systems to carry out these cryptographic tasks, what can we do? And I'm going to do, basically the talk's divided into three parts. I was going to give a broad introduction to quantum information and try to get a little bit of a hands-on view of some of the models that we use to understand information in that realm. And then I was going to give two examples from my own work about this, the project of mapping out the theoretical possibilities. So one is device-independent random number generation, and the other is two-party coin flipping. They're related in that they both involve generating random numbers, which is a fundamental task in crypto, but different in that the first topic, device-independent topic, is where I prove that something is possible. The second one is where I prove that it's not. So in either case, it's kind of refining, narrowing that boundary between what we know we can do and what we know we can't. But both of them involve using mathematics in ways and asking new mathematical questions. Okay, and I designed this talk to be expandable, so please feel free to jump in and ask questions whenever you like. So starting with the introduction, so I'm gonna start with the big picture and then kind of gradually close in on those two research topics that I mentioned. So quantum information, what this means in a broad sense is that we're taking quantum physics, which is the physics of very small systems, like when you get down a little smaller than the size of an atom, a new kind of physics takes over. And what we are doing is we're using that new kind of physics to encode and manipulate information. And this is sort of the conceptual slide that I always begin with. Digital computing is based on bits. We have this data element, it has two basic states, and we work with that. We can apply gates to 1 bit, we can apply gates to 2 bits, and that allows us to build large algorithms. Randomized computing, in kind of a crude sense, we could think of as being based on random bits, and I've modeled these here by just a line segment. So what I'm saying here is like, so this point here that represents a bit that is definitely 0. This is a point that this is a bit that is definitely 1. The midpoint would be one that is 50-50. It's randomly chosen. It's either 0 or 1. And then, you know, if we go a quarter of the way over, then we have a bit that has 3/4 probability of being 0 and 1/4 probability of being 1. So basically, each point on this line segment represents what we'll call a state. And then, so if we accept that as a model, then quantum computing is based on not this one-dimensional model, but a three-dimensional ball. So it's kind of like we have added in all these extra states that have these exotic properties. So it includes the states we had before, including these random bit states, but it includes more than that. And it's these points that are outside of that line segment that have these exotic quantum properties that allow us to do things we couldn't do before. And I just wanted to point out for context, so as people may or may not know, there is actually a National Toy Hall of Fame, and in 2008 they inducted the Stick. It took them 10 years to do that. The Stick was actually one of the members of the National Toy Hall of Fame, and then in 2009 they went ahead and inducted the ball. So it took them 1 year. Computer science, it took quite a bit more. So some fields move faster than others. So delving a little bit into this model, I want to say a little more about what I mean when I say that states of a qubit are represented by a ball. So there's a meaning basically to every point on or inside of this ball. Each of them denotes a state that the qubit can be in. So we already saw that the qubit, if the qubit is in state 0, that refers to 1 point on that ball. And if this qubit is in state 1, that refers to another point opposite to that. And then if the qubit is in either 0 or 1 with equal probability, but we don't know which, that would correspond to being right at the center of the ball. And then for those who have heard like popular science versions of quantum physics, you will hear people say stuff like multiple states at the same time. So we can talk about a case where the qubit is actually in both 0 and 1 simultaneously. So, you know, they talk, for example, about a photon being in 2 places at once. And let's see. Oh, I just noticed there are some questions. Okay. So the question was, are the states of the qubit discrete? So the answer is no. These are actually continuous states, and you can literally describe them using like a 3-dimensional Cartesian coordinate system. So you can locate a point using 3 real numbers, or you can use complex numbers, it's equivalent. You could use 3 real numbers to describe where you are inside of this ball, and that is the description. So it's continuous rather than discrete because those parameters are continuous. Okay, so there is a precise meaning to describing states where the qubit is in both 0 and 1 simultaneously. So I'd say what that refers to is these points that are on the great circle between 0 and 1. So really to nail down what state you're talking about, you actually have to be more specific. You have to say how it's superposed between 0 and 1. But the common way of referring to a quantum property as being, in both 0 and 1 at the same time, these are the states that refers to. So in a sense, these are kind of the most quantum states, the most non-classical states that are out there. Okay. Is this analogous to fuzzy logic? I actually don't know much about fuzzy logic, but I would be interested to know the answer to that if anybody in the audience knows. Okay, so continuing the analogy to digital computation. So it's a qubit is like this is a data register, and it's in some state, and that state corresponds to a point on the ball. Now, if you're wondering how we actually represent these things, what it basically is, it's typically a physical property of a particle. The qubit we're referring to just as the abstract data, but when we're actually manipulating it, we'd be working with some physical property of the particle. In quantum crypto, the most common model that I've worked with so far is the polarization of a photon. I guess somebody just mentioned 3D movie glasses actually, and that's an example of the use of polarization. The polarization that a photon is in can be described by a qubit, and so in a sense in quantum crypto, what you actually do to carry quantum information from one point to another is to send. You can send a photon with that particular polarization. There are two basic types of operations that can be done on quantum systems from a theoretical angle. One is that you can do unitary operations, and in the case of qubits, that corresponds to just rotating this ball. And so quite literally, you just choose an axis running through the ball, and you rotate around that axis, and that causes the state to change. And then the other thing you can do is a measurement. And these are important in particular because this is how we get from quantum information back to classical information. So the simplest kind of measurements would take place on a qubit. What you would do is you would choose an axis, again, running through the qubit. And basically when you measure, you are forcing the state into one of the two endpoints. So there's these two antipodal points that you have selected by this axis. The state has to move into one of those. And where it moves depends randomly on its location in the ball. So, and there are mathematical formulas for this, but basically how it behaves depends on how close it is to 0 or to 1. If it's very close to 0, then it will probably move to 0. If it's very close to 1, it will probably move to 1. The probabilities are exactly proportional to the lateral distance from those points, 0 and 1. And but one thing that is maybe a little unique about this is every time you do the measurement, if you recreate the state and you do the measurement, it's going to make an independent random decision. So if this were the state, then maybe sometimes it'll move to 0 and sometimes it'll move to 1. And no matter how much you may know in advance about the setup or anything, quantum physics postulates that you won't be able to predict which way it's going to move. Okay, so that's single qubit physics. Given 2 qubits, we can perform unitary operations on those. Those are unfortunately a little harder to visualize. Before we were working in 3 dimensions. If you start talking about qubits, then you're in much higher dimensions. I don't know, something like 7 or something like that. It's a little harder to visualize, but you can still write it down using matrices. And that allows you to create these joint states, which also are a little harder to visualize because they're no longer represented just by single points within the sphere. And you get these exotic states that are called entangled. And what it means, if two particles are entangled, that means you could separate them and perform individual measurements on them, and you would get these, possibly get these exotic superclassical correlations that you would not be able to reproduce with ordinary digital technology. And we're going to see some specific examples of that later. And although quantum computing is not the focus, this is a good opportunity to point out where quantum computing kind of comes from. So I was already saying that, when we start to get into 2 qubits, things get complicated. If you get into n qubits for n, to be like 100 or 1,000, this gets very complicated because the size of the space that you're working with becomes exponential in n. And the result is that these operations quickly become too hard for any known classical algorithm to simulate. And that is sort of the basis for quantum computing. That is why there's interest in figuring out, well, if quantum systems can do things that classical computers, as far as we know, can't do, then how can we exploit that to solve new computational problems? Okay. But we're interested in cryptography. So the question is, why is quantum information useful for cryptography? Quantum cryptographers have lots of answers for that. My answer, which is tailored to this particular application that I'm going to be talking about, is this idea of intrinsic randomness. So we were saying before, if I prepare a qubit in this perfectly superposed state and then I measure it, it's going to make a random choice every time. And nothing would stop me from just redoing that experiment over and over again and just generating a sequence of truly random numbers. And we need randomness in cryptography, and here is one reason why. So these researchers went on the internet and did an experiment where they collected keys using RSA and that type of algorithm, and they didn't break them with Shor's algorithm because we can't do that yet. What they broke them with was because they were insufficiently random. And if you have insufficiently random keys, then you've got trouble. And there's some neat mathematics behind that too. Really, just like I think it's part of the problem is if you have two numbers that have a common factor, it's very easy to factor them both. Or, if they're each a product of two primes, and one of those primes they have in common, then Euclid's algorithm will very quickly break them both. And so in this case, the lack of randomness was a security problem. And they refer to that as a wake-up call for the need for better secure random number generation. Quantum physics could be very good for this because of this idea that no adversary, no matter how much information they could know in advance, would be able to predict the outcome of these hypothetical experiments that I was talking about, this way of generating truly random numbers. So that gives us a goal, and that goal is to find sources using quantum information, find sources of provable random numbers with minimal assumptions. And this idea of provable is kind of unique, I'd say, to quantum. It's hard in some contexts. It's hard to actually prove that you have random numbers. So, for example, if you're using a pseudo-random number generator, we know that's not really random. That's why we call it pseudo-random. Pseudo-random number generator would take a small seed that's believed to be random and then blow it up into a much bigger data set using some deterministic algorithm. From an information theoretic point of view, that's not really random, although people postulate that it is computationally equivalent. But this type of proof that we're looking for is of a different nature. We want actual physical proof, just saying if we believe the postulates of quantum mechanics, then there's no way that anybody else could have predicted these numbers. And we have the method I discussed for doing this, which in a sense accomplishes that. The only problem is it requires very strong assumptions. So I described an experiment where you prepare this very delicate quantum state perfectly superposed, and then measure it, and then just repeat that over and over again. That is not the easiest thing to enforce in a realistic setting, because you would have to get the state preparation just right, and you have to get the measurements just right, and you have to trust that the adversary is not somehow influencing you with that. And people, who do crypto probably know a lot more about that side than I do. But yeah, it's basically, we want to avoid those strong assumptions, and we want to be able to generate random numbers in a way that has a different trust model that makes fewer assumptions. And that is basically the motivation for both of the research topics that I'm going to cover. Any other questions at this point? Okay, so someone asked, does it seem likely at any point in the near future that we develop enough of an understanding of quantum behavior to break the randomness of quantum measurements? That's a good question. Physicists could probably give you a better answer. I would say, it seems there is strong experimental evidence that suggests that we are not going to be able to do that. And some of that evidence was supplied just in the last 5 years. They did something called a Bell experiment, where they separate two entangled photons at a distance and then measure them. And they find these exotic super classical correlations from that. And the thing is, you could prove from that experiment that one of two things must be true. Either there is some true randomness in there that will never be explained by any additional theory, or information is traveling faster than the speed of light between those two stations. So it basically comes down to that dichotomy. And it's physicists believe that Einstein was right, that information can't travel faster than the speed of light. And so that gives us solid support for the idea that this randomness really is intrinsic and isn't going to be explained by a new model. Any other questions? Okay, so stepping into the first research topic. So what I'm going to do is I'm going to present a different model, one that requires less trust, less assumptions, and try to use that to generate random numbers. So the model that we refer to as device independent, that is the model where we are dealing with devices and we are treating them simply as black boxes, or green boxes in this case. But anyway, they're boxes and we're just ignoring anything that goes on inside. And treating them as classical input and output devices, classical information goes in and classical information comes out. And we're going to try to prove stuff about what we get from various protocols with that completely black box picture, without making any assumptions about what's really going on inside. So realistically, this probably wouldn't be the case. I mean, you don't necessarily just get a black box that you plug numbers in, from the company and just do it that way. Realistically, Alice might have, an actual device in her lab that she, can look into and see the individual components. But what we're saying is she just ignores anything that she knows about it. And just, you could literally, in the lab, you could actually just like draw a mental box around a particular collection of devices and just say, we're totally hands off. We're not going to trust anything that's going on within that box. We want to be able to prove security anyway. And the question is, can we do that, and can we get provable random numbers from there? And a starting point from this is it's actually that Bell experiment that I was just referring to, this idea that you can achieve these weird superclassical correlations. And here is an example of this, how we test this weird superclassical behavior. So I'm going to say I have two of these mystery boxes, and I'm going to have them play a game, a two-player game in isolation from one another. And the way the game is played, I choose a random bit for each of them, and I feed them that random bit, and then they give me back each a random bit. And these bits we're calling A, B, X, and Y. And then we score the results of that based on this Boolean formula. It's basically so this is x XOR y equals a and b is basically what we're doing. So either this Boolean formula is satisfied or it's not, and the game is won or lost depending on the outcome. And the reason that we will find this useful for manipulating these mystery boxes is that, at least if you're using a digital device, if they're using digital algorithms, there is no way to win this game perfectly. And it's a good exercise to try to prove that on your own. Fortunately, in this case, algorithms that would describe the behavior of a box in this case are pretty simple. There's only two possible behaviors because there's only two possible values for the input A. And even if you can introduce randomness, but that doesn't actually raise the score. So you can prove just kind of using a parity argument and by referring to this truth table that there is no way to win perfectly. The best the boxes could do is win 3 out of 4 cases, 3 out of 4 possible values for A and B together. But if you have quantum entanglements, you can actually do better than that. So if we were to have, let's say, 2 qubits, and the assumption is one of these qubits is stored by one of the devices and the other is stored by the other device. And they may have been shared before the game was played by quantum communication. So we allow communication before the game, we just don't allow it during the game. You can choose the entangled state, and you can also cleverly choose measurements so as to maximize the probability that they're going to satisfy that Boolean formula. So basically, we're entangling this in such a way that if I make any measurement in this plane in the same direction on the 2 qubits, I will always get the same results. And then if I tilt one of the measurements a little bit, then I'm likely to get the same result. It may not be exactly the same. And if you recall in this picture, the goal is that the inputs should always agree unless A and B are both 1, and then they're supposed to disagree. So we can kind of rig something that approximates that behavior by saying, okay, I'm going to make the measurements performed on 0 fairly closely aligned. And same for 1, 0 and 0, 1. But I'm going to skew it so that if the inputs are both 1, then they're actually not so aligned. Then they're more like opposites. And you set the angles so as to maximize that behavior. And what you end up with is actually something better than what the classical players were able to do. So this number here, it's an algebraic number. It's like something like 1/2 plus square root of 2 over 4. You can get it just by referring to the formulas for these qubit states, and it's a good roughly 0.1 better than what any classical algorithm could do. And this gives us 2 things. So one is that it is giving us a way of sort of verifying that quantum physics is real, that entanglement is real, and that it can't be simulated by some other behavior. But it also gives us a way of generating this kind of certifiable randomness, because if we observe this kind of behavior, then we're able to say, well, something random must be going on, because if everything was determined in advance, we would be looking at classical behavior and they would have to satisfy this bound. So this is sort of the initial unit, the initial building block for putting together some kind of certification procedure for generating these random numbers. Okay, so device-independent randomness. So what we do is just sort of a repeated version of this CHSH game. We take these 2 boxes and we play the CHSH game many times over and calculate the average score and just look at where that lies. So I'm saying the score is 1 if the players win, and the score is 0 if they lose. And okay, so say we play 5 times and the score is 0.8. Technically that's higher than 0.75, but maybe they just got lucky. That doesn't tell us much. However, if I repeat this many times and they're still consistently landing above 0.75, then classical statistical arguments will tell you that that is extremely unlikely if they are exhibiting classical behavior. So what that allows us to conclude is if a certain threshold is broken, if it's substantially above 0.75, then except with exponentially small probability, some kind of random behavior is actually taking place. And this is sort of where one of these mystery properties in quantum is giving us something that we couldn't otherwise do. So out of this completely black box model where we don't know anything internally about the behavior of these devices, we're still able to conclude something just by observing from the outside. And in this case, we were able to determine that there is some randomness going on inside the devices. So an idea that was proposed by Roger Kolbeck back around 2007 was that we take this and we try to use it to efficiently generate a large number of random numbers. And so we go further, we don't just say partially random, we come up with some procedure that's going to give us uniformly random, where the adversary has virtually no information at all about the numbers that we get from these devices. And here is an example of that. This is an example, sort of a diagram of a protocol that you could use to generate random numbers in that fashion. So technically, this is not random number generation, it's randomness expansion, because you start with some initial random numbers and then use those to produce a much larger amount of random numbers. And here's how that goes. So I'm going to say, I'll take these two black boxes, and I'm going to play the CHSH game with them, but I'm going to do it in an efficient way. I don't want to be using a lot of initial randomness because that's expensive. So what I do is every time I want to run the devices, I will flip a highly biased coin. So with a very small probability, I will play the CHSH game. With a much larger probability, I won't play the game. I will just give input 0, 0, because that doesn't require any additional randomness. And the boxes never know which one you're going to be using. Then after it's all over, score the game rounds only. Don't need to worry about the non-game rounds. The rounds on which the game occurred, figure out how well it did on average at the CHSH game. And then, based on that, then you see if that's substantially above that 0.75 threshold cutoff. If it is, then you say, okay, we've succeeded. Now we take the numbers and we do something called randomness extraction. Randomness extraction is basically a procedure for taking numbers that are partially random and compressing them to numbers that are uniformly random. And yeah, so that's the black box procedure. And the idea is if we make delta small enough, then we have used a lot less randomness than we have arrived at once the procedure is over. Okay, and it's a topic that a lot of people have worked on over the years. There's a lot of great work on there. Our accomplishment on this was that we proved that this works, and also that it is that not only that it works, but it's also uniformly random, even with respect to an entangled adversary. So in the strong sense that the adversary herself might have entangled information with those devices, the numbers are still random. And that's useful, particularly if you want to compose this with other protocols. Now I will include, I have 2 math slides in this talk. So, I'm coming from the math angle, and I will just briefly mention sort of the key innovations and the results that kind of get us to where we need to go. So very often in this case, it's like we can write down the model, but we need some special insight in order to figure out the proof that everything actually works. And in this case, it had to do with matrix norms and vector norms. So there's this special thing called the Schotten norm of a vector, a Schotten norm of a matrix. It is basically different ways of measuring the length of a vector in complex vector spaces, and it's just given by this formula. So if p equals 2, you have ordinary Euclidean length, which is more familiar, but if you change p, then you get kind of a distortion of that shape. And then you can define the same thing for matrices by looking at their eigenvalues. This is easy to compute. This is not so easy to compute, and it's also not so easy to prove things about. So it turned out that the magic ingredient in the result that I just quoted was actually having to do with the shape, the overall shape of this particular norm. There was, I remember, so I was working on this and I was thinking like, you know, there's some property of this norm that I need, and somebody somewhere has probably proven it. I just don't know where. And after some literature searching, we found it from like 20 years ago. Somebody had proved that the norm has this particular rounded shape for matrices. And and in a sense, I mean, this is, you know, I'm explaining the project from two pretty different angles here, but in a sense, this gap, when you average two matrices and you take the norm, you find that that norm is smaller, and it's this gap that actually introduces the randomness. That's what allows us to prove that the randomness builds up when we are carrying out the protocol. Okay, so so that was sort of the math side, and I did also want to mention, since we're talking about kind of the current impact of quantum developments, that this has been realized in experiments over the last few years. Multiple teams have done it. This was one particular case where we did it, and the idea was, so the black boxes in this case are sort of like stations that are separated within a building. I think this is NIST Boulder here. So this would be the first box, this would be the second box, and you choose random measurement settings at those locations and use the spatial separation and that speed of light limit that I was referring to establish that no communication takes place. So that is something that has been put into practice, building on previous physics experiments. Okay, so that is device-independent randomness, and I'll pause briefly again for questions. Okay. All right, so I think we're on pretty good track with the time. So the next segment, I got about 10 slides for. This is also related to random number generation, but it is random number generation with a different type of model. And we are asking similar questions about under what conditions is random number generation possible. So instead of this single user black box model, we're now going to look at a multi-party model where you have two users, and now the problem is that they don't trust one another. So before it was that Alice didn't trust her devices, now it's that Alice doesn't trust Bob, and vice versa. And we're looking at a kind of fundamental boiled down scenario in which these two mutually mistrustful parties have to do some cooperative task together. And what they want to do is simply, they want to generate a random bit, and they want it to be fair, but they don't trust the other person to do it. So, you know, this is like the coin toss at the beginning of a football game. We're going to assume that Alice wants this random bit to be 0, Bob wants it to be 1. If they had a trusted third party, they would just ask that trusted third party to flip the coin for them and tell them what the result is, and then they'd be satisfied. But we're assuming they don't have that. And somehow between the two of them, they've got to come up with a coin flip where they can both walk away, you know, being satisfied that it was a fair coin flip, even if it doesn't come out in their favor. And we want to do that with quantum communication. And if this is known to be impossible classically, we want to do it quantumly. So basically, we allow them a dialogue where they exchange quantum information, and then at the very end, each of them says what the coin flip was, what they think the coin flip was. We want it to be the case that if they behave honestly, if they do what the protocol tells them to do, then these bits will always agree, and they will be a perfect coin flip together. On the other hand, we need to guard against dishonest behavior, so we also want to say, if Bob is dishonest, but Alice is honest, then Bob still can't bias the results too much in his favor. So specifically, he would want, so we're going to ignore his output because he's being dishonest, so it doesn't matter. We would assume he would just give output 1. What we want is to make sure that he can't deceptively trick Alice into giving output 1 with probably more than 1/2 plus epsilon. And similarly, symmetrically, if Alice tries to trick Bob, she shouldn't be able to fool him into giving outputs 0 with probability greater than 1/2 plus epsilon. So it's still that basic idea of trying to recapture the intrinsic randomness of quantum, but here it's harder because we have to deal with this kind of adversarial behavior, the idea of an adversary who is trying to manipulate things on their side of the system to get to change the randomness. And we want the honest party to be able to stabilize it and still get a fair result. So previous results on this started formally in the 90s. I think it was proposed as early as the 80s, but they started in the 90s. There was a progression of results where they started showing that you could do this, and this sort of trade-off appeared between how good that bias figure epsilon is on the one hand, and also the complexity of the protocol, and particularly the number of rounds of communication that's necessary in order to get this security guarantee. And this is one of the cases where I think it's very interesting from a mathematical standpoint, because the first few protocols were very simple. I mean, you could actually just write down matrices that describe exactly what Alice and Bob are supposed to do, and then just prove based on formulas, manipulations of those matrices, that you have the security guarantee that you want. But after that, in order to bring the bias lower, because ultimately we want the bias to be very small, like 0 or very close to 0, there were much more complicated protocols that started to be introduced. And so Carlos Muchon did some great work on this between 2004 and 2007. And he started introducing all these unexpected, I would say, mathematical tools in order to get better and better protocols. And then there's this, this phenomenal paper that he posted on the archive in 2007, I think about 80 pages long, where he proved that you can actually get all the bias all the way down to 0, which is pretty remarkable. The downside was, at that point, the protocols were so complicated, you get this figure here for the total number of rounds. And this is a very big figure. So what I've written here, this is basically like, you're taking a number and raising it to itself. So, you take, 20 to the 20th power, that's very big. And it grows incredibly fast. And so this was it's a theoretical result, but hard to implement practically because it would require so much communication going back and forth between Alice and Bob. So that was 2007, and sort of the question that remained that ultimately motivated the next result that I was going to present was why we seem to have hit this wall, and we haven't been able to improve on that, because ultimately we want just a simple protocol that Alice and Bob can carry out. So how many rounds are actually necessary? So Muchon established that you can do it with this huge number of rounds. How many do we really need? There was one previous result that showed this lower bound for the number of communication rounds. And this is a pretty slow growing lower bound, no problem. If we could actually find a protocol that matches that, that'd be great. It left a big question mark, this and Muchon's result left a big question mark about how many we actually need in order to carry out coin flipping. So if we, from a cryptographic standpoint, ideally we would find that n is no bigger than the order of log of 1 over epsilon, because that's cryptographic security. That would be saying that the bias vanishes exponentially in the number of rounds. That would be pretty good. We could also settle for polynomial in 1 over epsilon or linear. Both of those would be things we can work with. The thing that I ultimately proved, I was ultimately setting out to prove one of these things. I ultimately proved that actually neither of these is possible, and that it has to be exponentially large in 1 over square root of epsilon. And so there's a reason that Muchon's communication protocol was so big. And so the result is we find that the situation is triply exponentially worse than it was before. So it's an example of necessary complexity, and it's a little surprising because it was a pretty simple task, And we know it's a task that is possible to do, but we have discovered that it actually requires exponentially many resources. So like on the last slide, I'll just briefly highlight the math tool that allows this to actually be carried out. So, and this is another case where I was working with the mathematical model and kept running into this this question, this like math question, and figuring somebody somewhere has probably resolved it. So in the as part of the proof of this result, I show the following. If you have a rational function that has a highly concentrated pinched shape, then, so meaning it's very large at one point, so very large right there, but bounded, tightly bounded elsewhere outside of that small neighborhood. If it has that tightly pinched shape, then its poles have to be exponentially large. And just for the mathematicians, I wrote down what that means. So basically, if this behavior is tightly constrained like this, let's say between 0, 1, -1, and 1, then that necessarily means it has wild, large behavior elsewhere. So the poles shoot up very quickly once you're outside of that interval. And it turns out the reason this is useful is that this quantity over here, the size of the poles, is actually related to the number of communication rounds in a certain protocol. So in a sense, it's because of this exponential blowup that we ultimately get an exponential lower bound on the size of communication. Okay, all right, we were aiming for 50 minutes. I think we're doing pretty well. So, so summing everything up, kind of putting that all together. So quantum technology from the perspective of cryptography is both a threat and a benefit, and it offers us threats, but also offers new ways of doing things with a different type of security. New developments within quantum crypto involve advances both on theory and in experiment. And so one way they can happen is that theoreticians will map out the space of something that, that is possible and prove that it's possible. And then that theory can then be implemented in experiment. And these theoretical advances often happen by finding the right mathematical question to ask. So we may start with a model, a mathematical model that's particular to the problem that we're working with, and just keep reworking it and distilling it until it comes down to a very simple mathematical problem. And then either find the right person or the right paper to answer that question.